Hi, everybody. It's on. How's everyone doing? My name is Casey Bodley. I am at COHORTFS, working on NFS on top of Ceph. So the title is Scalable Metadata over NFS. So why do we like NFS? It's IETF standard. So there's a lot of implementations out there. It's well established. There's a client available on all the major platforms. And it's extensible. And it can adapt to future needs, such as data. So there's many techniques for scaling data. You've got RAID and object striping, crush for placement. So what can NFS do to take advantage of those techniques? That's parallel NFS. PNFS was introduced in NFS 4.1. And it allows PNFS clients to speak directly to storage devices. So PNFS has different layout types for block volume devices, OSDs, which speak T10. And the file layout is a generic layout that uses the NFS protocol. So you can basically run an NFS server on top of your storage device. And that's what it looks like. Instead of having a single single NFS server. Thank you. You have one metadata server, which serves layouts and metadata. And you have your array of storage devices, data servers. So a PNFS layout is state given by the MDS that describes how a file is placed on the devices. There's a layout get and layout return, and the MDS can recall it with layout recall on conflicts or changes to placement. And there's a consistency via layout commit. So you do your writes and commits to the individual data servers, and then layout commit to the MDS will update the size, the metadata. And so PNFS is optional. If something isn't working, if you can't get your layout, if a write to a data server fails, you can always fall back to the MDS. So what about metadata? We still have just the one MDS. And there are workloads that will stress that, like large directories shared by many clients all trying to read it. Workloads that create lots of files and operate them on many threads. And so systems like Ceph have techniques for scaling metadata, distributing it, and load balancing. But NFS doesn't have a way to take advantage of that currently. So this talk is about PNFS metastripe, which takes the ideas of PNFS and applies it to metadata. So you can mount an initial metadata server and get layouts which direct you to the other metadata servers where your files and directories are located. So we are working on an IETF draft for PNFS metastripe. It defines two layout types. One is for the striping of files, so finding out where an inode is located in your cluster. And the other is directory striping, so finding where a directory entry is going to be. So as I said, the client mounts the initial MDS and is directed to the others. So the Filehandle Striping Layout is a single layout that covers the entire file system. So that differs from the PNFS case where you get a layout on an individual file. And we use NFS file attributes to provide hints to the client about where the file is placed. And that allows the client to talk directly to the MDS that is authoritative for that file. So because it's based on hints, we don't have to recall this file handle layout on changes to placement. So directory striping is the other, possibly more interesting one, which describes how directory entries, names are striped across a directory. So right now, it's just simple hashes over stripes. We'd like to add support for Ceph fragtrees. But this one is a layout per directory. It's recalled on changes to placement. And when you create a directory, you can give hints for how it should be striped, how many files you expect to put in it. And so the operations that we can take advantage of in metastripe are a preaddir, which allows the PNFS client to read all of the stripes in parallel. So the normal readdir uses cookies to index into the directory, but those are all separate for each stripe now, so the client's in charge of enforcing the ordering to support taldir and seekdir. Other operations are directory modifications that we can do in parallel. And we use layout commit to provide consistency for these. So we can send bulk creates, renames, removes, without having to update the inode's time. And on layout commit, we restore the consistency. So this gives us parallel operations. So the prototype that I've developed for Metastripe is based on the open source NFS Ganesha server available on GitHub. They have existing support for Ceph. And for the client, I'm using the PyNFS test suite, which is a Python implementation of NFS with a lot of great testing. So I developed a set of tests for all of the Metastripe operations that's available on Linux NFS. And so this is what the prototype looks like. Each metadata server has an instance of Ganesha and the Ceph MDS. And the MDS talks to the Ceph components as usual. And it's driven by the PyNFS client. So changes required for libcephfs, which is the client library for Ceph that Ganesha links to, provides callbacks on changes to the MDS map so that Ganesha can track where the metadata devices are and provide layouts on them. And it also gets callbacks on directory placement for restriping events so that it can update the directory layouts. And so changes in the Ceph MDS to support this, since the original draft does not support Ceph's fragmentation. We replaced Ceph stir fragments with simple stripes. We added per stripe locks instead of inode locks so that we can operate on stripes in parallel. And for M-time updates, we do asynchronous updates, and they're batched. Let's see. And we use these cap updates for the stripe locks instead of invalidates so that the client can maintain its cache instead of blowing out everything on changes. So for the parent stats, which is the time, the size information, and the recursive stats for quotas and stuff are done asynchronously. They're queued up in the MD cache's pre-dirty journal parents function, and they're sent in batches to the MDS that's auth for that inode. So since they're asynchronous, it only provides weak consistency for the directory time. Layout commit is what's going to sync it, but that is incomplete at the moment. In terms of caching, by adding capabilities to the stripe locks, we allow the client to cache the directory entries for each stripe independently, and they are not invalidated when the inode changes. And for the cap updates, we send those synchronously on changes so that we update clients. For example, adding and removing files since their last cap update allows them to stay synchronous or consistent. So future work, looking to implement the layout commit and get the time consistency right, and add support for Ceph fragtrees both in the IETF draft and to implement the Ceph MDS in terms of that. So we're going to leave Q&A until later, but that's all I've got. Thank you very much.